Veronica de las Reyes from Bachelor of Secondary Education major in Mathematics at Kapalong College of Agriculture Sciences and Technology, and I am a third-year college student. And for today's video, we will be discussing about the application of differential equation, specifically in Newton's law of cooling and the law of growth and decay. We will be discussing first the Newton's law of cooling. According to Newton's law of cooling, the rate of loss of heat from a body is directly proportional to the difference in the temperature of the body and its surroundings. Newton's law of cooling is given by the change in temperature d uppercase T with respect to time, or d uppercase T over dt is equal to k times T sub T minus T sub S, where T sub T is equal to temperature of the body at time T and T sub S is the temperature of the surrounding. K is equals to positive constant that depends on the area and nature of the surface of the body under consideration. Let's proceed to its formula. Newton's law of cooling formula is expressed by uppercase T times T is equal to T sub S plus T sub O minus T sub S times e to the power of kt, where T is the time, uppercase T times T is the temperature of the given body at time T, T sub S is the surrounding temperature, T sub O is the initial temperature of the body, and K is constant. Example: the temperature of a body dropped from 200 degree to 100 degree for the first hour. Determine how many degrees the body cooled in 1 hour more if the environment temperature is 0 degree. Solution: let the initial temperature of the heated body be T sub O is equals to 200 degree. The further temperature dynamics is described by the formula. Uppercase T times T is equals to T sub S plus T sub O minus T sub S times e to the power of negative K times T. So we have T sub S plus 200 degree minus T sub S times e to the power of negative K times T. At the end of the first hour, the body has cooled to 100 degree. Therefore, we can write the following relationship. So we have uppercase T times T is equals to 1, which is the first hour, is equal to 100 degree equals to T sub S plus 200 degree minus T sub S times e to the power of negative K times 1, which is the first hour. And the next is 100 degree equals to T sub S plus 200 degree minus T sub S times e to the power of negative K. After second hour, the body's temperature becomes equal to x degrees. We have x is equals to T sub S plus 200 degree minus T sub S times e to the power of negative 2 times K. Thus, we obtain the system of two equations with three unknowns, the T sub S, K, and X. We have 100 is equals to T sub S plus 200 minus T sub S times e to the power of negative K, and the X is equals to T sub S plus 200 minus T sub S times e to the power of negative 2 times K. We cannot determine uniquely the body's temperature X after the second hour from this system. However, we can derive the dependence of X on the environment temperature T sub S. Express the function e to the power of negative k from the first equation. E to the power of negative k is equals to 100 minus t sub s over 200 minus t sub s. Hence, e to the power of negative 2 times k is equals to the quantity of e to the power of negative k raised to 2 times the quantity of 100 minus t sub s over 200 minus t sub s raised to 2 times t sub s. Then the dependence x times t sub s has the form x times t sub s is equals to t sub s plus 200 minus t sub s times the quantity of 100 minus t sub s over 200 minus t sub s raised to 2. So we have x times t sub s is equals to t sub s plus the quantity of 100 minus t sub s over 200 minus t sub s raised to 2. If, for example, the surrounding environment temperature is 0 degrees, the body's temperature x in 2 hours will be x times t sub s is equals to 0, which is the 0 degrees is equals to 0 plus 100 minus 0 squared over 200 minus 0 is equals to 10,000 over 200. So we have 50 degrees. So 10,000 over 200 is equals to 50 degree. Therefore, if the environment temperature is 0 degrees, the body's temperature x in 2 hours will be 50 degrees. The next application of the first order differential equation is the law of growth and decay. It is the rate at which the substance's changes is proportional to the quantity of substance present at any time. To put it mathematically, we have an equation dx over dt, change of substance x with respect to time, is proportionate to the quantity of substance present at any time. So we have this as dx over dt is equals to k times x as a rate equation. And if we're going to solve the general solution of this differential equation, we arrive this equation where x is equals to ce to the power of k times t, where x is the quantity of substance present at any time, t is the time, k is the proportionally constant. For example, a herd of llamas has 1,000 llamas in it, and the population is growing exponentially. At time t is equals to 4, it has 2,000 llamas. Write a formula for the number of llamas at arbitrary time t. Solution. Here there is no direct mention of differential equations, but use of the buzz phrase growing exponentially must be taken as indicator that we are talking about the situation of x is equals to ce to the power of k times t, where here x is the number of llamas at time t and k are constants to be determined from the information given in the problem, and the use of language should probably be taken to mean that at time t is equals to 0, there are 1,000 llamas, and at time t is equals to 4, there are 2,000. Then, either repeating the method above or plugging into the formula derived by the method, we find c as the value of x at t is equals to 0. So we have k is equals to ln x sub 1 minus ln x sub 2 over t sub 1 minus t sub 2 is equals to ln 1,000 minus ln 2,000 over 0 minus 4. So we have ln 1,000 over 2,000 minus 4 is equals to ln 1/2 over negative 4 is equals to ln 2 over 4. Therefore, x is equals to 1,000 times e to the power of ln 1/2 over negative 4 times t. So we have x is equals to 1,000 times 2 to the power of t over 4. And that's conclude my video tutorial. Thank you for watching. Bye! Stay safe everyone and God bless us all.